Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we'll cover 3D particle equilibrium. And in my experience, this is probably the most important tutorial you guys will see because this is the most closely related question to a midterm question of all the tutorials so far. And the reason why is because it takes a lot of concepts that we know and combines them into one. The first being particle equilibrium, which we did in the 2D cases, so that was kind of more of a warm-up for this. But then, as you guys will see for 3D, it's not as simple as just using cosine and sine to find all your components. A lot of the times you'll have to dabble into actual vectors. And that's where week 2 comes into play, where everything we learned about the unit vector, position vectors, we will need that in order to find the components for 3D. And it makes things kind of tricky, but again, this is very important because all the midterms I can recall have the particle equilibrium question is always a 3D case. And some stuff will kind of vary in it, but it always is a 3D case, so it's good to know 3D. But as you guys will see, even though it's a little tedious, it's not too bad as long as you kind of follow the steps. And we'll go through the steps very clearly and in much detail. All right, with that being said, let's begin. Alrighty, so looking at this example, what it would like us to do is to determine the maximum weight of the crate so that the tension developed in any cable does not exceed 450. And it says pounds, but I just swapped it to newtons. Like I said, we're going to try and keep things in SI units here, just make it a little bit easier. So also in the diagram, we're just going to delete all these feet and just pretend that it says meters instead of feet. Okay, so even though all these say feet, we're just going to pretend that it says meters. Nice and easy. So, equilibrium in 3D. I know that we've done a lot of practice in 2D, and what's nice is all the concepts stay the same for 3D. Just some little tricks that you guys are going to want. So before we begin, let's just kind of do a bit of a review, find out what we're solving for, find out how we should solve for it, stuff like that. So, real quick, particle equilibrium in 2 dimensions. We know that everything is based off of 2 equations, and those are the summation of the forces in the x direction has to be 0, and the summation of the forces in the y direction must also be 0. Remember, we said that the number of equations that you have is the number of unknowns you can solve for. So since in 2D we have 2 equations, we can solve for 2 unknowns. However, now we have a 3-dimensional case. Okay, 3D, well, those 2 equations still have to apply. We can't have any unbalanced forces in the x or y direction or else something's going to move. However, we have that 3rd direction to consider now, the z direction. So in 3D, there's going to be a 3rd equation, summation of the forces in the z direction is equal to 0. And these are the only 3 equations you're really going to need to solve these problems in 3 dimensions. Now, they become a lot more complex because finding components of a force in 2 dimensions is easy. You usually give it an angle, or let's say a triangle, and from there you can easily find the components. For example, in this case right here, I'm just going to highlight this because we're going to talk about the 2D case. So I'm going to just focus on these 2 right here. Remember, these are from 2 dimensions. They also apply for 3 dimensions. But in 2 dimensions, if we have a grid as so, and we go across, make a nice axis, and we know that our y-axis is here and our x-axis is here. There's only really 2 scenarios that you can really have to get vectors. So if this was a vector, we can either do 2 things to you guys. We give you a vector like this, or let's say we give you a second vector like this. And finding the components, again, 2 ways. 1, we give you an angle. So for this vector right here, what we can do is we can give you an angle here. We know that the components of that vector, so let's just label this one f1. We know that f1x, so the x component of 1, is going to be equal to f times cosine of theta. And similarly, for f1y, so the y component, we know it's going to be equal to f times the sine of theta. So, nice and easy. In the second case, they can really give you for 2 dimensions, and even though it may look more complex, it's actually the nicer of the 2 cases is when they give you a triangle. So when they give you a vector, and they give you a little triangle on top of the vector, and then they give you the dimensions of that triangle. So let's say it's 3, 4, and 5. In this case, and we'll call this vector f2 so you guys can know what I'm talking about, we know that f2, x in this case, is going to be equal to the magnitude of f multiplied by 4 over 5. We're just taking the horizontal component of the triangle and dividing it by the hypotenuse. It's really, really simple. And similarly, we know that f2y is going to be equal to the magnitude of f times 3 over 5. So again, really nice and easy. And for 2D, these are the only real cases that you're going to have. So finding the components is really simple. The hardest part in 2D for students is usually just solving those equations, especially if there's a trick involved, such as a pulley or a spring, where you may have to do a little bit of extra work or make extra assumptions. But now, unfortunately for you guys, the midterm's probably going to be 3D, because the 3D can test everything. The 3D can look exactly like this. For example, they could also maybe, from A and B, they can put a spring here. The same concepts still apply. The hardest part about 3D now isn't really knowing the tricks, but getting your components of each of the forces, because three-dimensional forces, of course, they're going to have 3 components. So I'm just going to erase this because we're not dealing with springs here. But now we're going to talk about the third equation. So what's very, I don't know the word, bittersweet is that third equation. It's nice because having an extra equation allows us to solve for an extra parameter. And again, that's nice. The more things we can solve for in engineering, the better. The bad part is you guys are going to have to solve for that extra parameter, so you guys are going to have extra work. So it's nice from an engineering standpoint, but from you taking this class, probably not the nicest. But here's the trick, and this is what you guys are going to want to pay attention to, is how do we get the components of the forces easily? That's the trick, easily. We don't want to be spending a lot of time on these. We want to try and do it nice and simple, nice and quick. So how do we find the components of forces in 3D easily? Well, there's going to be 3 situations that you guys can have. 3 situations. So the first situation, which I like to call, I just call it the trig situation. So I'm just going to put trig, and it's a very specific case where what they're going to do is they're going to give you a nice 3D axis like this. So excuse me while I take my time to draw something beautiful. Alrighty. It's probably still not the best, but of course in 3D we have 3 components. We have our x, our y, and our z. And what they can do for this is they're going to give you a vector, say in 3D, that goes something like this. Now, there's 3 ways, or 3 scenarios you guys can see for trying to find out this vector. The first one, like I said, is trig, and that's when they give you 2 angles, very specific angles. They're not just out of the blue. And then one of them is when you come dot, 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 and then dot, 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 dot. So one of the angles is going to be with the vector and the XY plane. Oh, so I drew that wrong. Sorry. One of the angles, I'm going to do it in a different color so it really stands out, is going to be between the vector and the XY plane there. So I'm going to call this theta. Because what happens is this is actually comprised of 2 vectors. The first one right here, which goes straight up, like so, and then one that comes basically from the origin into the XY plane to that point. So this one that goes, well, I use this loosely because it depends how you define your direction, but the vertical vector, this right here is going to be your f, z, and I should probably label the first vector as f. F. So from here, we can find 2 vectors. The first one, fz, and then the second one here, this vector is actually going to be called fxy. Because it's not the x vector, it's not the y vector, but it's in that xy plane. So from there, we can find the component in the xy plane. And it's very nice to solve for because we know that f1, or I guess it's not 1 anymore because we're only going to talk about 1 vector. We know that fz is going to be equal to the magnitude of f times the sine of theta. And similarly, fxy is going to be equal to f times the cosine of theta. So this gives us two components, but again, what we want is x, y, and z. So out of this, we only have one of the three that we need, and that's f of z. However, what's nice about this too, is I'm going to do this in purple, is that vector in the xy plane, the fxy, it's also comprised of two vectors. Those being fx, which goes along the x-axis. That's not really well along the x-axis. I'll draw it on this side. So there's fx that goes along the x-axis. And this will, of course, not be to a very nice scale, but we got fx. And then we have fy. Oh, that one also looks bad. All right, how can I draw this better to scale? I should have put the vector in a nicer spot. Is what I should have done. All right, so I'll do it this way. So we got like this. It should be parallel to the x-axis. And this right here is going to be fx. And of course, we have a vector running along the y-axis, fy. And right in there, which I'll draw in maybe green, they'll give you that second angle. And this angle right here, we'll call it phi, so we don't get it confused with theta. So what we can do in this special scenario is we can say, okay, we know fxy, which is basically the hypotenuse of that triangle. So we can later deduce that fy in this case is going to be fxy. So that's the trick here. It's not just f anymore. It's fxy times, of course, in this case, it's going to be times cosine of phi. Now, you guys have to be extra careful because sometimes they'll give you the angle in relation to the x-axis and not the y-axis. And if that's the case, fy will be fxy times the sine of phi. So just pay attention to that. And then, of course, fx in this scenario is going to be equal to fxy times the sine of phi. Perfect. So this is the first scenario. Again, I call it the trig scenario because that's basically all you're doing is you create two little triangles, and from those triangles you can start to solve everything. Now, will this be on your midterm question, the trig scenario? Probably not, because what we want to do is test you guys on 3 dimensions. And this isn't really testing you guys on 3 dimensions. This is testing your ability to make things into 2 dimensions. So will trig be on the final? Or sorry, the midterm? If trig's on the final, oh, that'd be scary for you guys. Trig be on the midterm? Probably not. Just because, again, we can't really test trig very well. It doesn't really cover the concepts of 3D, such as the unit vector, stuff like that. So this one, I'm just going to put in brackets. And again, I don't make the midterm. But I'm going to put probably, that's the keyword, probably. That's probably spelled wrong. Probably not on midterm. Again, it doesn't really test your 3-dimensional capabilities, but if you want to find the components, that'd be how, nice and simple. So we're going to scroll down, new page, we're going to go 2, and the second case, which I can really see being on the midterm because there's a really, really good trick with it, but don't be scared. It's the easiest of all the cases, even easier than trig, and that's when they give you coordinate, direction, angles. Oh, that's a long word. Coordinate, direction, angles. So if I were to draw another beautiful xy plane, or sorry, not xy plane, but a 3-dimensional space. Perfect. So we have y here, z here, x here. This is the case where they can give you a vector, and I'll put the vector in red, why not? And they give you 3 pieces of information, or they can give you 3 pieces. There's a little trick that it'll probably be less than 3. It'll most likely be 2 pieces of information, but we'll get to that after. What they'll do is they'll give you 3 angles. First angle is going to be from the vector to the positive x-axis. I'm going to say that again, to the positive x-axis. And this right here is alpha. The second one they're going to give you, we'll do it in pink, could be from the positive y-axis to the vector. And it's called beta. And similarly, the last angle, which I'll do in blue, will be from the positive z-axis to our vector. And we'll call this one gamma. And of course, we should probably just label the fact that this is our force vector, F. So this is the nicest case, believe it or not. because what we can do is easily, and I say this, I'm going to emphasize this, easily find the unit vector of this vector. The unit vector of this vector. Oh, it sounds terrible, but it's easy. Because what we're going to do in this case is we're going to utilize the fact that our force vector is going to be equal to the magnitude of the force times the unit vector of that force. Okay, well, just by looking at those angles, it's not very apparent what the unit vector is, but here's the trick. Remember that for one of the components, we're just going to start with alpha. We know that cosine of alpha is equal to fx over f. Oh, okay, well now we're kind of getting somewhere. Oh, this is the magnitude of f. I should probably put that in. Okay, well, all I'll have to really do is rearrange this to get fx is equal to f times cosine of alpha. And that's all you have to do. That's all you have to do. It's nice and simple. So for this scenario, what you can state is that fx is going to be equal to f times cosine of alpha. F2 is equal to f times cosine of beta. And that's not F2, sorry, I'm an idiot. That's Fy. So our Fy is going to be equal to f times cosine of beta. And Fz is going to be equal to f times the cosine of gamma. So, Clayton, you're going to ask me, you think that this is a good midterm question, but it's so easy. You have those angles, very, very simple. Well, it is very simple. And if you get this, be happy, because it is as easy as it sounds, but there's two tricks that can get you. Just two tricks, so if you pay attention to these tricks, you'll be good to go. The first one, which I'll have to write again, I'm terrible at writing, the angles must be, and I cannot stress this enough to you guys, the angles must be with the positive axis. So angles must be with the positive, axis. So if they give you an angle, and I'll do this in a different color here, I haven't used green. So let's say for the x-axis, actually no, let's go for the z-axis real quick. If they give you this angle here, from this f all the way down to here in green, you cannot use that as gamma, because it's to the negative z-axis. So what you're going to have to do, and it's very simple, you're just going to go 180 degrees minus that angle, it'll give you gamma. So it's very easy to account for, but it's a little trick that if you're not paying attention, you can use the wrong angle, and then things will start getting messed up. Now, that's probably the simpler of the two tricks. It's very easy to kind of keep track of if it's going to the positive or negative axis. Here's what gets students the most. And this, I'm just going to put number 2. I'm going to put the problem, so the question itself only gives 2 angles. So the problem gives 2 angles. And that becomes very problematic for students who don't know about this trick. Let's say in a question that you get this question, f is your vector, and what they do is they do this. They give you alpha and beta and say, find the components. Okay, well, x component, f cosine alpha, easy. The y component, f times cosine of beta, again, pretty easy. But what about the z component? And that's where a lot of students will start getting really tricked. But don't worry. What you're going to have to realize is that identity that we talked about. It's the fact that cosine of alpha, and this is the squared, plus cosine squared of beta, plus cosine squared of gamma is equal to 1. You have to remember that. Because in this scenario, there's really 3 variables. You got the 3 angles. So if the problem gives you 2 angles, say above here, they gave you alpha and beta. Well, we know alpha, we know beta, we can solve for that gamma. So that's the little trick, is if they give you two angles, you go to this formula, you can solve for that unknown angle, and then find the rest. And even though it sounds really simple, a lot of students forget about this. So it's just easy way to kind of trick students is give them this scenario, give them two angles, and then they have no idea how to solve for the third component. And of course, in equilibrium, you're going to need that third component to solve any equations. So you miss that third component here, well then you're kind of hooped for the rest. So I like this question. I can see it on a midterm. It tests a good understanding of what you know about the coordinate direction angles, which is what we want. You guys need to show your understanding of 3D. I'm just going to put this angle back in so we know that it's here. This one would be gamma. So this one, really good. I like this one. So please pay attention to this one. Now, I can see this as not being the main force. So we look up at the question here. What do we have? We have basically, we know we're going to have four forces acting at point A, one for every rope. So that coordinate direction angle, I can't see it being all the forces. They gave you the coordinate direction angles. First of all, it would look terrible because that would be 3 angles for each force. We got 4 forces there. That'd be what, 12 angles in a little space? They're not going to do that. Of course not. What I could see them doing is giving you coordinate direction angles for one of the forces, say AB. Okay, well, AB real quick, we can hammer that out quickly, we're good to go. However, now we're going to get to the main case, case number 3. So we're going to scroll down all the way to our new page, and we're going to go case number 3. And as you guys have probably already guessed, based on what you guys already know about 3D, because again, 3D is not new to you guys. You guys know what you're doing. You guys know how to find the force in Cartesian vector notation. So the third case, probably most obvious, what we're going to do is give you coordinate points. Coordinate points. Now, this case is this case is probably the least straightforward case. Up in this case, well, if we look here, I'm just going to highlight, we have an actual expression for f of x is equal to something. If we look up here, we have again another expression, f of x is equal to something very specific. In this case, we don't really end up with an expression saying f of x is equal to something. This is when it's going to actually test you guys and your knowledge of vectors. And it's very important. This is why this question is probably the most popular, and this is probably why you'll see this one. This one tests your knowledge of vectors. Now, I'm probably shooting myself in the foot by saying all this stuff to you guys because if a professor was to watch this and going, oh, this guy is really hyping them up for this case, maybe we can screw them and throw in the trig case, they might just do that. So, again, this is how I think, this is what I believe, but know all 3 cases. It's not a guarantee that this will be the case. Again, as a kind of disclosure, I do not create the midterm. I do not create the midterm. I just watched you guys suffer through it. All right, so the third case, coordinate points. So again, what I'm going to do, I'm going to draw a nice plane so I can show you guys exactly what I'm talking about, even though you guys are probably like, Clayton, we know, we've done this already. You don't have to do it again and again and again. Well, I'm going to because why not? So we got X, Y, and Z. Sorry, X, Y, and Z. Kind of speak for a second. And what they're going to do is they can give you a vector, let's say that goes like this. Just like this. They give you an arrowhead, and what they can do is they'll throw in 2 points. So they're going to have a point here, and have a point here. They'll say that this is point A, and that this is point B. And a lot of you right now are going to go, oh, why'd you label it like that? It's clearly going from the bottom up. So shouldn't the bottom be B and the top be, the bottom be A and the top be B? Well, they can label these in the midterm however they want. I threw them like this because it's going to start testing your guys' knowledge. So when you get a case like this and you want to find the components, you're going to want to really utilize this relationship. The force vector is going to be equal to the magnitude of the force times the unit vector. This is going to be your savior. This is what's going to make this very, very simple for you guys. Again, this will not result in simple equations like before where you get f of x is equal to something, f of y is equal to something. This will be a little bit more, you guys are going to have to kind of figure it out by yourselves. But I'm going to show you guys how right now. So, again, we want to utilize that relationship. The magnitude of the force, right here, in these questions, well, that's really your unknown. Equilibrium is about solving for the magnitude of forces. So this is going to be on your unknown. Well, usually you're not also going to get this, the force vector in Cartesian vector notation. So this will also be your unknown, because you can't solve for it because you don't know the magnitude. So now you're going to start saying, okay, well, two unknowns, why are we really doing this? And it's because of that unit vector at the end, which I'll highlight right here. And it'll become very apparent, very, very apparent why we're trying to find that. But let's just take a step back, and how do we find that unit vector when we have 2 points? Well, we're going to have to use position vectors. You guys already know this. It's very simple. Position vectors is where it's at when we're trying to find a unit vector in 3D. So what we're going to do is we're going to say the position vector here. And for this case, remember, position vectors, you have to put in the specific notation. This one goes from point B to point A. So we're going to put in that order from B to A. And that's equal to the coordinates of A minus the coordinates of B. So again, another easy way that students get tricked up in the midterm, they go, okay, RBA, so it's RB minus RA. Well, no, it's the opposite. You want to take where you end up and subtract your initial position. So from there, we'll get a nice vector. And then with that nice vector, so RBA, we can find the magnitude. And I didn't draw that line very nicely. We can find the magnitude just right from what we calculate above, because that's going to be equal to the square root of RBA comma x squared plus RBA comma y squared plus RBA comma z. So again, this is the exact same as a force vector. The formula for finding the magnitude does not really change. Perfect. So now that you know these two values, you can easily find the unit vector u is equal to, it's going to be the position vector, so RBA, divided by the magnitude of RBA. So far this shouldn't be new to you guys. You guys should be experts at this. So finding that unit vector, that's what we want to do. Because then we can go up to our equation here. So what we're going to have is we're going to have our force vector is equal to the magnitude of the force. And what I'm going to do real quick is I'm just going to substitute the magnitude of the force. Well, we don't know it. We're just going to say it's the force times the unit vector. And what I'm going to do for fun here is I'm just going to put this in kind of brackets. And this will not be always the values. I'm just going to put random values. Just random values. I'm going to say, let's say our unit vector is equal to 0.32i minus 0.72j plus 0.45k. Now again, your unit vector will probably not be those values. Don't think it's always at the same time. And I'll probably should just label this. I'm just going to put sample numbers. Everybody knows that these aren't always the numbers. So sample numbers, just to show you guys what exactly we're going to do with this unit vector. So if we have our force vector, and again, that's our unknown, that's F. We just know that it's F. In the case up here, and we were to look at FAB right here, well, our magnitude is just going to be FAB. We don't have a number for it. We're trying to solve for it. So our magnitude we would just leave as FAB. But we go down here, and what we can do is we can take that F and multiply it into the unit vector. So if we were to do that, what we're going to do here is we're going to get 0.32. Actually, I'm going to do it a line below just so I have more room to show you guys. So this will be equal to, brackets, 0.32, and this will be F. And that's in the I direction. Minus 0.72 F in the J direction. So again, I'm just taking that F and multiplying it into the unit vectors. Unit vector, singular. There's not more than one. And then plus 0.45 F in the K direction. Okay, well now you just got a vector. You still don't really have the components but we actually do. And this is where this case is the hardest for students because of the intuition. It's right here. This right here, this I component, that's going to be our fx. And I'll switch colors. This component right here, this is going to be our fy. And then finally, our last component, which let's do blue. This right here, this is going to be our fz, or z, or z. I also know that my z or z's, I don't know which. Well, you guys can say it however you want. they look like twos, so be ready for that. I'm sorry if I start confusing you guys. So that's the real trick to this one. Again, it's a very common scenario because it really tests your understanding of position vectors, unit vectors, but also tests your understanding of why we do Cartesian vector notation. And again, it comes down to we can find the components, but we don't really have a specific formula per se that says fx is equal to this. What we can do is we can find our force vector in Cartesian vector notation with the magnitude as a variable or an unknown. And then from there, we can say, okay, that's our fx, that's our fy, that's our fz. And what you guys will see later is in the example, I'm going to find all of those force vectors in their Cartesian vector form, again, with the magnitude unknown. And then when I'm doing my summation equations, all I'm going to do is I'm going to take all the I components, sum them up to 0. I'm going to take all the j components, sum them up to 0. And then what's different about 3D, that third component, the z component, well, in that case, I'm going to take all of the k components, sum them up, it should be equal to 0. So I know that was probably an extremely long introduction to this, but again, I hyped this up in the last videos because this right here, it's almost always your midterm, guys. I'm being honest with you guys. This is almost always your midterm, three-dimensional particle equilibrium. And I've kind of told people that usually the first question in the midterm, again, this will be question number 2. The first question is just going to be testing your knowledge on 3D vectors. First question is usually nice in the fact that it's split up into a lot of sections, part A, B, C, and D. Part A is saying, find the force vector in Cartesian vector notation. Part B, find the unit vector of this vector. Part C, find the angle between vectors. It's split up into all those parts. These ones are a whole different monster because usually what happens is they're just going to say, solve the tension in all the cables. It's not split up into those parts. And what's bad about that is a lot of your marks will just be on your final answers. It's not going to be split up where you can kind of get those nice, easy part marks that, well, you guys are still new in university, but you'll learn that part marks is where it's at. You guys just want part marks. Part marks will save your butt. But in this case, it can be very scary because you go right to the final answer. There's no really intermediate steps. So we're going to go through this example now. And hopefully this can really clear a lot of things up. I know, again, this can be long, but if you guys don't want to watch any of the other videos for week 3 and just focus on this one, that's fine. Just remember that what they can easily do, and I'll do this in pink, is they can throw a spring here for AB. Well, it's the same thing, because once you find that force in the spring, which is what we'll, the force in that cable, we can use the force equation of a spring to find out either the constant of the spring or how much it deformed. Or let's just say that there was a pulley here. Well, we know that that force actually stays the same. It just changes direction, stuff like that. So the concepts that we talked about in 2D are easily, and I really mean this, easily applied to 3D. So if you see a spring, you guys already know what to do. We covered it in detail. You guys know how to deal with springs. All right. So with that being said, let's kind of get into the question right here. So I'm going to go down, and we wrote a lot already. So I'm going to just put problem here so you guys know when we actually start the problem. I know that we're, what, half an hour in and we haven't even started the problem. I'm sorry if you guys think it is a waste of time. Alrighty, so particle equilibrium problem. The first thing that we always have to do, and this applies to 3D. I know a lot of you are thinking, oh, well, maybe not in 3D, but yes, 3D, free body diagram. And yes, 3D, well, the thing with 3D is if I look at this free body diagram, it's basically the picture. There's not a lot of real difference, but you still have to do it in 3D. Even if there's not a lot of difference between the picture they give you, you still have to do your own free body diagram because that's a very important concept that will be expanded upon in much more. And I can't emphasize when I say much more detail in the coming weeks, especially after the midterm. So we're going to go down here, and the first thing I like to do with free body diagram, I'm just going to draw some nice axes real quick. So I'm going to go down, I'm going to go across, and finally I'm going to make something that goes like this. And again, free body diagrams doesn't have to be perfect. Don't worry, guys. I'm not an artist. As you guys see, I'm getting my butt saved by the fact that Notability allows me to make straight lines. If not, this would look horrendous. So what I recommend for you guys, though, for straight lines, the bookstore sells little rulers, and they're only like 15 centimeters long. They're really nice, easy. That's what I recommend. I don't know how to say this. Kind of the janky way to draw straight lines. If you're ever in a scenario, use your 1 card. Lots of people use their 1 card for straight lines, so that's another possibility. So first thing about this axis, I'm gonna have to label which one's the positive. So of course we got our Z, Y, and our X. And if we look up here, particle equilibrium, we know everything's gonna happen at a certain point. If we look here, that point right there is actually gonna be A. Everything kind of happens at point A. So what I'm going to do here is I'm just gonna make my particle at the very bottom, and I'm just gonna highlight this, because that's where kind of everything happens. And from there, I can draw all my forces. So just what I remember, I know that there was a force going along the x-axis, and I'm going to just choose a brighter color so it sticks out more. I'm going to do the forces in red. So you know that there was a force along the x-axis. I remember that there was a force going straight downwards on the z-axis. And then that there's 2 other forces. One of them kind of went in this direction, and the other one kind of went in that direction. So again, I don't really have to have the directions perfect, as long as the general direction is fine. But again, free body diagrams, a lot of things you have to consider. The first of which, you have to label the forces. You have to label which ones we're talking about. So I'm going to have to go up and check, but I know that the one going down, I remember that was the weight. So again, that was the weight. I'll start at the one at the very bottom here, AD. So what I'm going to do is, I know that this force, all the way down, this right here is going to be F, AD. I'm going to go up to the top and check the other 2. I know the one at the very top goes from A to C. On the left side goes from A to C. So all the way back down here, I'm going to write F, AC. And this is equal to F, AB. And usually what we do for particle equilibrium is we want to include angles. Remember 2D, we throw the angles or the triangles for everything. Well, we can't really do that for 3D, but what we can do, and what you guys should do, is put all the coordinate points. So we know that the origin is 0, 0, 0. The weight, well, we know that that just goes straight down. This point over here, I believe it was 3, 0, 0. So 3, 0, 0. And for the other 2 points, we're going to have a point here and a point here. We're going to have to kind of find those. And that's kind of nice because, again, the end goal of the free body diagram, you should be able to solve the question just by looking at your free body diagram. And if we actually have those coordinate points ready instead of all those dimensions that it has in the actual picture, we should be able to solve the problem much more quickly. So we're going to go up real quick and look at point B. And just looking at point B here, we're going to start off with the x. Well, we know it's actually 2 meters, but in the negative direction. And then the y is going to be 1 meter, and then the z is going to be 2 meters. So it's going to be -2, 1, and 0. -2, 1, and 2. See? That's why you have to pay attention. So we got -2, 1, 0. And you should probably put the units, of course. I'm an idiot. So those are in meters. And then FAC, and I put 0. I'll go change it when I go back. It's going to be -2, -2, and 1. So we're going to look down here. I'm going to go -2, -2, 1. And if you guys don't know where I got those from, I think it's best if you guys just kind of go look for yourselves, because that is a very important skill, finding out where those coordinates are and then relate them. So if that's the case, you have the coordinates here, just pause the video, go back up, check, because finding those coordinates will be very, very, very important. Get the coordinates wrong, I'm sorry, you're going to get everything else wrong. So that right there, free body diagram. It has all the information I need to solve this problem. But a lot of you, of course, are going to go, well, you don't really dimension where the weight ends up. Well, since we know the weight's in the z-axis, we know that this vector is just going to be in the negative k direction. But we'll get to that a little bit later. So we got our forces, got our free body diagram. Now we can kind of analyze, well, what situation are we looking at here? So we go up here, and you go, okay, well, I don't have the angles between the planes and the axes, so that's probably not trig. Again, don't have any angles, so it's probably not coordinate direction angles. Oh, I got a lot of points. And this one talks about coordinate points, so this is where it'll be at. Coordinate points, again, it's the best test in my opinion. Make sure you guys know everything. And if that's the case, what we want is we're going to want our force vector in Cartesian vector notation with the magnitude as the unknown. So we're going to go up here real quick, or I guess down here, and we're going to start. So what we're going to do is we're going to go, I'm going to do all the position vectors together and then all the force vectors together. I'm not going to find the position vector of AB and then the force vector AB and then position, force, because to make this simpler in the end, as you guys will see, it's nice to have all three force vectors right beside each other. So I'm going to find the position vectors of everything first, as well as their magnitudes, and then their unit vectors, and then I'm going to go on and find the force vectors. So let's just start real quick, and we're going to go with, let's go AB. So RAB, remember, it goes from A to B. It's going to be the coordinates of B minus the coordinates of A, which is going to be equal to, and we're going to do here, -2, comma 1, comma 2, minus coordinates of A, which are 0, 0, 0. Okay, well, that should kind of look really nice and easy because basically RA is all zeros. So the position vector RAB, what it's going to be in the end is it's just going to be -2I plus 1J plus 2K. So it's really just the coordinates the coordinates of B. And that's kind of a nice little trick if your starting point is the origin. Now, I'm going to say that again. Starting point is the origin. It may not be the origin. If that's the case, you can't just go right and make that assumption. If it's the origin, though, you should be good to go. And we're going to put meters. And what's nice is our other vectors real quick right up here. We see that they also start from the origin, but we'll get to that later. So I found the position vector. Another thing I'm going to want to find real quick is just its magnitude. So RAB, the magnitude, because it's in those absolute value signs, is going to be equal to the square root. I'm just going to square all those components on the inside. So we're going to have 2 squared plus 1 squared plus 2 squared. And what we're going to get in the end, 3. 3 what? Well, it's position vector. We know that the units are meters, so this must also be 3 meters. And what this means physically on the diagram is the distance between points A and B. If I were to take a tape measure straight from those 2 points, the distance is going to be 3 meters. And I'm highlighting that with you guys because a lot of questions, when they want to give you a magnitude, they'll never give you that symbol, RAB, the magnitude is equal to this. In the question, what they'll do is they'll say, the distance between points A and B is 3 meters. So they won't actually give you any mathematical symbols. They're just going to say the distance between these points is 3 meters. And it's up to you guys to go, okay, well that means the magnitude of the position vector between those points is 3 meters. So, good to know. And finally, what we can do is we go with the unit vector, AB. We know all it's going to be is position vector, AB, over the magnitude of AB. Just put our nice division sign. So what I'm going to do here is I'm just going to take all those components and divide them by 3. So we're going to have -2 over 3 in the I direction, plus 1 over 3 in the K direction, and then plus 2 over 3 in the K direction. I'll change that after. 2 over 3 in the K direction. This is not the K direction. This is the J direction. J direction. So notice how that I still make those simple mistakes going slow. So can you guys imagine when you're in the midterm trying to rush through this? It's usually what happens. So we found our unit vector AB. We can easily find its Cartesian vector notation. But again, I'm going to hold off on that till the very end because I want to have all those vectors right beside each other for when I'm doing my equilibrium equations. So RAB, done. Let's go RAC now. RAC is equal to, and we know that's just going to be the position, the coordinate points at C because we're starting from the origin. So it's going to be negative 2I minus 2J plus 1K. And this will have units of meters. We also know that the magnitude of AC is going to be equal to 3 meters. So you guys can check that, but what I noticed is if we look at our position vector, we have a 2, and a 1. And if we look up top to RAB, it's also a 2, and a 1. So if they're the same, they're going to have the same magnitude. We can kind of skip a little bit of time, a little bit of a time saver. So from there, we can just go right to the end, and we know that our unit vector from A to C is going to be equal to, and I'm just going to divide all those components by 3. So we're going to have negative 2 over 3 in the I direction, minus 2 over 3 in the J direction. I just about put the K direction for some stupid reason again. And then plus 1K. Remember, unit vectors don't have units. Even though it says units in the name, it has to do with the fact its magnitude is 1. It doesn't mean it has units. So 2 vectors down so far, not too bad. You guys already know what we're doing. This is kind of more review at this point. Last one that we're going to want is RAD. And now this one's kind of interesting, and I'll show you guys a little bit of trick at the end for this. But let's just pretend that we don't know. We know that RAD is going to be equal to the coordinate points at D, which is 3I plus 0 J. That K is really messing with my head now. I have no idea. And plus 0K. That's in meters. Now, we know that the magnitude of RAD is going to be equal to the square root of 3 squared, which is equal to just 3 meters. Because we're just squaring it and then square rooting it, we're going to get the same. Okay, so now what we're going to find is the unit vector AD is going to be equal to, it's going to be 3 over 3, so it's going to be 1I plus 0J plus 0K. Now, I did 3 steps to get there. Position vector, the magnitude, and then I did the multiplication in, or the division. However, if we were to look at this diagram, that force is directed along the x-axis. So we actually didn't need to do that work because we know, just from our intuition, that if something goes directly along the positive x-axis, its unit vector is going to be 1, 0, 0. For instance, if a vector was going along the y-axis, just purely along the positive y-axis, its vector is going to be 0, 1, 0. So we didn't have to do that work. It was kind of unnecessary. What you guys can do is just recognize it goes along that axis, skip straight to the unit vector. Say this is what the unit vector is going to be. Nice and easy. And finally, that trick is what we're going to do for the weight here. So we know that the unit vector of the weight is going to be equal to, it goes right along the z-axis, so it has no x or y components, so it's going to be 0I plus 0J, and it's going to be plus 1K. Or I didn't want to say plus. I was going to ask you guys, but I probably already spoiled it. It would be 1 if it was going up in the positive direction, but our weight's actually going downwards. So what it's going to be right here is minus 1K because it's going in that negative z direction. So now that we have all our unit vectors, we can start beginning to find our force vectors really, really simply. We know that FAB is going to be equal to the magnitude of FAB, which we're just going to have as FAB, because that's how it's labeled in our free body diagram, times the unit vector FAB. And what happens when we multiply this in, we're going to get this. We're just going to take FAB and apply it to everything in that unit vector. So if we look at our unit vector, the first component is negative 2 over 3I. So we're going to get negative 2 over 3 FAB, and that's in the I direction. we're going to go up to the j component. It's plus 1/3. So we're going to have plus 1/3 FAB. And that's in the j direction. And finally, we're going to have plus. We're going to go up to the top again. It's 2/3. So what we're going to do is plus 2/3 FAB. And this one's in the k direction. So I'm not going to put units in newtons at the end here because the FAB has units in newtons, so it's kind of already taken care of. What you guys are going to want to realize later, and I'll use it in different colors, this first part right here, that's going to be our FAB in the x direction. And I'm going to keep these colors consistent for the other ones, and I'll show you guys how we add them together in a bit. But this one's going to be FAB in the y direction, and then we'll do this last one in green. This one's going to be FAB in the z direction. So that's how we find our components. So it's really not too bad, but if you're kind of forgetting about your position vectors, it may be a bit of a challenge. So we're going to move on to the next one real quick. We're going to go FAC. FAC. Well, we know that's going to be equal to the magnitude, but we know that it's just an unknown. Sorry, that's an unknown. And it's FAC. We're going to multiply by the unit vector AC. So what we're going to get in the end is going to be equal to, I'm just going to skip up to the unit vectors real quick. We got FAC as first component negative 2/3i. So what we're going to have is negative 2/3 in the I direction. But we have to multiply it by FAC. And that's in the I direction. We're going to scroll up to the next component over here. Going too far. It's again negative 2/3 minus 2/3 FAC. And this one's in the j direction. And finally, we're going to have plus 1/3 FAC in the k direction. Alright, so now we got two of the vectors already. And again, what I'm going to do is I'm just going to highlight these real quick. So when we add the vectors later, you guys will know exactly where to get these values from. It's going to be FAC, comma x. The next color, what was it? Pink. Highlight this real quick. This one's going to be FAC, comma y. And the last one, what was it? Green. Was it the lighter green? No, it was not that green. That is almost too bright. All right, so we're going to go across. And this one, of course, is going to be FAC, comma z. Or z. I'm very inconsistent with how I pronounce that. Alrighty. So we know we have two more vectors. Going black. Perfect. So the next one, we're going to go FAD. And now it gets easier. Those were kind of the more time-consuming ones. We know it's going to be equal to FAD times the unit vector AD. And what we're going to get is that it's equal to, and we're going to go up and just check real quick. Well, we know unit vector AD is just one I, basically. So this one right here, I'm just going to put it's equal to FAD in the I direction. And then you can stop it here if you guys want, but I like to put 0j plus 0k. Just to kind of keep things in order. Because I know what I do if in the x direction it's fine, but let's say it was only in the y direction. I'd have FAD I, or sorry, j. And I know that I may easily mistake that for an I. So I always like to keep this order to kind of remind myself, okay, these components are the ones that are 0. This is the one I have to consider. And now finally what we can do is the last one, which is going to be the weight vector is equal to, of course, the weight times the unit vector of the weight. And this is actually a best example of what I was just talking about. Is for this one, instead of just going minus WK, I'm going to go 0I to remind myself there's nothing in the I direction, plus 0J, and then minus W in the K direction. So real quick, I'm just going to label some stuff right here. We know that there's something in the x direction, so I'm going to label this in purple. So we're going to have FAD, comma x, and then green. And then we know that there's also a component of the weight. So we got the weight in the z direction. Alrighty, so now we have all our components of all of those forces, and they're all unknown. So what we can do now is apply our three equilibrium equations. Remember, since we're dealing with 3D, we have three equations. Number one, sum of the forces, or the summation of the forces in the x direction is equal to 0. So I'm just going to put in, I'll put in purple brackets here. That's all the purple components. So in case you guys are wondering, those are all the purple components. So if I go up to the top here, I got one for FABX, so we're going to have negative 2 over 3 FAB. Let me look up here. Well, we got one for FAC, which is also negative 2 over 3, so minus 2 over 3 FAC. And we also have one for AD, plus FAD, and that's the last one, so we know it's equal to 0. I'm going to go dot 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 equation 1. So again, to solve these equations, you're going to have to do some algebra. I'm going to label the equations now, so when I'm doing the algebra, I can easily reference what equation I'm talking about. So our next one, again, this is the same from 2D. Our summation of the forces in the y direction must also be 0. I believe I had it as pink. Yeah, it was pink. So this is all the pink components. Pink components. So when I do that, I'm going to go up to the top. Well, I got one right there, 1/3 FAB. So we're going to have 1/3 of FAB. Look at the top again. Well, there's also one for FAC, and that's negative 2/3. So minus 2/3 FAC. And if I look up, well, there's not any other pinks. So those are my only two components. Going to be equal to 0. All right, moving on. And this is where you guys are going to remember 3D. And it's right there in the word 3D. We should have three equations. And that's going to be the summation of the forces in the z component is equal to 0. And that right there, I believe, was green. So we're going to look at all the green components here. Perfect. So we're going to go up to the top. Check. Oh, well, FAB up here has a green component. It's 2/3 FAB. So 2/3 of FAB. Now we're going to look up again. All right, FAC also has one. It's 1/3 plus 1/3 of FAC. And then minus, of course, we know that the weight has a component going downwards, so minus W is equal to 0. And this is our equation 3, dot, 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 3. And I forgot to kind of label this as equation 2. Alrighty. So we have our equations. This is usually the last step that we usually find. Our equations are good to go. And we just solve the equations. But let's just take a quick step back and just check what we got as unknowns real quick. So actually I'll just write instead of highlighting. So for unknowns, if we look through the equations, so we'll look at equation 1 there. Well, we got FAB and FAC. FAB, you know, FAC is unknown as well. And also from equation 1, we know that FAD is unknown. Look at equation 2, it has FAB, FAC, but we already listed those. But if we look at equation 3, we also know that our W, our weight, is unknown. So I'm going to put in brackets here. These are four unknowns. So remember what I said. The only amount of unknowns you guys can solve is the amount of equations you have. And we only have 3 equations, but there's 4 unknowns. So this should be your hint. Either there's something you're missing, perhaps there's a spring. And in that spring, they give you the stretch of the spring as well as the constant. You can find that spring force very, very easily using the spring formula. However, what I like to do for the question is just go up to the top, check if there's anything. And in our question right here, and I wish, can I highlight a different? Oh, we can highlight in pink. And here's what's going to get you. Right here. If you see this word on your midterm, be scared. These are the questions that people hate the most. I'm not kidding. These are the ones people hate the most. Maximum. A maximum. And that should scare everybody. Because what that means is, who knows what those forces are? They could be anything. Literally anything. But what we know is that when one of those forces... Oops. I'm going to go back. Whoa, this one's a weird color. When one of those forces hits 450 newtons, so one of those cables, it's going to break. It's going to break. So we know that we're going to have to find the solution to this equation where one of the forces is equal to 450 and everything else has to be below. If we have a force that's equal to 550, well, it's already broken. It would never reach 550. So we have to solve this in terms of making sure that all those cables are equal to or under 450 newtons. And I talked about it in our last example, and it has to do with elasticity. So I'm going to go down here. I'm going to acknowledge that I got 4 unknowns, and it's an elastic system. So what elastic means is everything is proportional. Everything is proportional. If FAB is equal to 1 and FAC is equal to 2, okay, so the relationship is 1 to 2. If I increase FAB to 5, FAB is also going to increase to 10. It's always going to be proportional. So it goes from a 1 to 2 to a 5 to 10. So they're always going to be the same. So because of that, what I would recommend doing for this problem is I'm just going to take one of the forces, and I'm just going to take the first one on my list here, and I'm going to say FAB is equal to 1. Just nice and easy, FAB is equal to 1. I'm not going to put newtons, nothing. I'm just going to say it's equal to 1, because from there, I'll be able to solve the proportions of all the other forces in relation to FAB. So from there, let's say I get FAC, let's just say I get FAC is equal to 2. What I can do is I can say, okay, FAC will always be twice as great as FAB. So from there, I can say, okay, well, if I times the 2 by 250, I get that 450 newtons. That was our maximum. And I can do the same thing here, times 250, to get 250 newtons. So I know that FAC, when it's 450, FAB is going to be 250. And we'll kind of go through this after, but I don't know this yet. So what I'm going to do is I'm just going to start by saying FAB is equal to 1. And if I look up at our unknowns now, we know FAB now. Well, we don't really know it, but we have a value for it. 3 equations, 3 unknowns, we're good to go. So what I'm going to do is I'm going to start off with equation 2. And what that is sum of the forces in the y, because what I get is 1/3 FAB is equal to 2/3 of FAC. And that's it. There was only 2 components. It's a nice one to start off with. So from there, I can just do some quick things real quick. I know that the 3's are on both sides. I can cancel them. And I also know that FAB is equal to 1. So just kind of writing this again, I know that 2 FAC is equal to 1. So from this, I can solve that FAC must be equal to 0.5. I just move the 2 to the other side. It's going to be 1 divided by 2. So now I have FAC. All right. So looking up here, we can go 2 steps right now. We can go to equation 1 and find FAD, or we can go to equation 3. Now, if we look at equation 3, and I'm just going to go back to the yellow highlighter, that has our weight in it. Remember, this weight, that's our final answer. That's what we want to find at the very end. So, a lot of you guys go, okay, well, we can solve for that weight right now. We're good to go. But we can't, actually. And the reason why is we need FAD. We don't need it to solve for the weight, but we need to verify that FAD will be lower than FAB. Because what happens if we solve for the weight and we'll get a value, of course. But then if we solve for FAD and that one turns out to be the critical force, the one that breaks first, everything changes. Everything changes. So for this question, we're going to have to go to equation 1 and solve for FAD. So if we look at equation 1 real quick, which is up here, FAD is already positive, the other 2 are negative. I'm going to throw the other 2 to the other side and go FAD is equal to, and I'm just going to look at the other 2 real quick. We got negative 2 over 3 FAB but it's positive since we moved it to the other side. So 2 over 3 FAB. The other one was negative 2 if I recall. So yeah, minus 2 over 3 FAC. So this one's going to be plus 2 over 3 FAC. And that's it. So what we can do is we can sub numbers in. So we're going to have 2 over 3. And FAB we say is 1 plus 2 over 3. And FAC we said is 0.5. And what we're going to get is FAD. I'll just do it in a different line here. FAD is equal to 1, which is perfect. If it was greater than 1, well, it's also fine because we can make the adjustments. But if you guys were to have assumed FAB was the limiting force, you'd be correct because it's the highest, or it's tied for the highest. So what I'm going to do now is I'm just going to kind of convert the forces into their actual newtons. So what I'm going to do is I'm going to make a little list. FAB, we got FAC, and we got FAD. And we know that the values for these are 1, 0.5, and 1. And what we want to do is we want to find a factor to multiply them by to get 450. Remember, that's the max value. So what we're going to see here is that FAB and FAD, they're both the highest. They're both the highest because they have the greatest value. If FAB was 2 and FAD was 1, then FAB is the highest, and that's the one we're going to focus on. But we kind of got lucky in a case where both of them are actually the exact same. So since they're the highest, we know that those are the ones that are going to break first. So those are the ones that we're going to want to convert to 450 newtons. Okay, well, how do I go from 1 to 450? Well, I just multiply by 450. All right, so those are easy. Well, what do I do with FAC now? Now remember, everything's proportionate. So if I multiplied FAB and FAD by 450, I'm going to also have to multiply FAC by 450. And what that'll give us is 225 newtons. So those are my forces now. Those are all my forces right there. So those forces are correct. Those are correct. And how do we verify that they're correct? Well, remember, the maximum load it can take is 450. And none of those forces are over 450. So we're good to go. Good to go. So now, knowing these forces, we can go to that equation 3. So I'm going to go equation 3 here, which states that the weight is negative. So I'm going to move the weight to the other side, is equal to 2/3 FAB, 2/3 FAB, plus 1/3 FAC, plus 1/3 FAC. And since I know the values of FAB and FAC, I can just substitute them right in. So it's going to be 2/3 of FAB, which we know is going to be the 450, plus 1/3 of FAC, which is 225. And we substitute all that in, we're going to get 375 newtons. And that's the end of the question. So what I can state now is the weight of the crate is 375 newtons. So, quick little thing real quick. If we look back up at the top of the question, which I'll do after I do the box here. So there's my box, final answer. We go all the way to the top. This is one thing you're going to have to pay attention to. I'm just going to erase it, but I'll highlight it again real quick, is the weight. So remember, weight doesn't mean mass. It's not asking for kilograms. Weight is a force. So what a question could do, and what this could do, which would be actually probably better for a midterm scenario, is they ask you for the mass of the crate. Well, if you know the weight, you know that the weight is mass times gravity. You can just divide that 375 by gravity. You're good to go. But if it asks for the weight, which is 375, and you put the mass, not only did you have to do an extra step that wasn't required, you get the final answer wrong, even though your weight was correct. So one of those things, make sure that you know what the question is asking you. It's very, very, very important. All right, so that's it for this example real quick. What I want to do real quick is just one other scenario. And I just want to show you guys elasticity one more time, because again, this is the hardest concept. So let's go back down here, and let's say that FAB is, we got the value of 1. FAC, we got a value of 0.5, so those stayed the same. But we got FAD, and we got a value of 2. We got a value of 2 that time. How does this change things? Well, like I said, the maximum force a cable can take is 450. So whatever number between those three is the largest, that's the one that's going to hit the 450 first. So in this case, FAB and FAD, all these A, B, B, blah, 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 FAB and FAD don't hit 450 at the same time. FAD does before FAB. So we know that this right here, FAD, that's going to be the 450 newtons first. So to get to that, what we're going to do is we're going to times by 250 to get that. So if that's the case, remember, everything has to be proportional. So we have to times the other 2 by 250, times by 250, times by 250. So our forces in this case would have been 250 newtons for FAB and 125 newtons for FAC. And if we look back at equation 3, that relies upon FAB and FAC, and FAD is actually the limiting factor, it changes our FAB and AC. So because of that, if we went straight to equation 3, we would have got the final answer wrong. So don't go to that final equation if it's a minimum or maximum, unless you know for a fact. Unless you know for a fact that your forces are correct. If not, everything can change really fast. We got lucky in that if you assumed FAB, it actually would have worked out for you. But that's not always the case, and probably won't be the case on a midterm scenario or anything like that. So that concludes this question. Like I said, this is a great question. Great question. This is, I'd say, midterm level difficulty. A lot of the problems I say, the midterm will usually be harder than this, typically. This one, I'd say, is as hard as a midterm question because of that fact that it's a maximum. If it didn't say maximum and it gives you the weight of the crate, so let's say they rearrange the question so that they say that weight is equal to 300 newtons. Solve for those three forces. It'd be pretty easy. So what they would probably do in that scenario is make, let's say, this one a spring. And the final question wouldn't be solved for the forces, although you would have to anyway. It would say, what's the stretch in that spring? Well, what you would do, you'd solve for three forces, and with that, you'd find FAD. And from there, you know that FAD is equal to the spring constant times the relative displacement. And you'll have to be given the spring constant so you can find that relative stretch in the spring, something like that. And you guys know springs, we already covered it, so you guys should be good on springs. I'm hoping so. If not, please review the videos. We talk in great depth about springs and how to deal with them. They sound scary, but they're very easy. So, I think that's all I have to say for this type of question. Again, probably going to be on the midterm. 3D. You review this, you should be good, hopefully. Alright, thank you guys so much for listening, and I'll see you guys when we start next week, which is moments. And basically what that entails is when all those forces, remember, right now they act at a single point, and here it was A. But sometimes they don't act at the same point. So the methodology, those three equations there, that stays the same. But we have additional equations to account for the rotation that a force will cause on a body. But I'll talk more about that when we start those videos. So thanks again, everybody. I'll see you guys in the next video.